Hello everyone, this is Braden, and today I will be presenting about reverberation mapping and the Sloan Digital Sky Survey. Quasars are some of the most luminous and energetic objects in the known universe. They are supermassive black holes in the centers of galaxies, surrounded by rotating accretion disks made of gas. As the black hole sucks up matter from the disk, friction causes the gas to heat up to millions of degrees, causing the accretion disk to give off radiation across the entire visual spectrum. This radiation then excites clouds of gas surrounding the disk, causing them to emit radiation of their own. This area is known as the broadline region, and there are various ways of measuring the mass of the galaxy's central black hole. We can do this by observing how fast stars and gas orbit the black hole, and in some cases, such as Sagittarius A star, we can even calculate its mass from the size of its shadow. But as quasars are located over 100 megaparsecs away from us, we cannot use these methods, so we must use a different technique known as reverberation mapping. Reverberation mapping is based on the same basic idea of observing the speed of objects orbiting the black hole. However, we cannot directly observe the broadline region, so instead we deduce its properties from the quasar spectrum. The spectrum of the quasar consists of continuum radiation from the accretion disks and emission lines from the broadline region. While the continuum radiation spans the whole visual spectrum, the broadline region radiates the emission lines of the excited elements within it. And on the left, I've got this image of a quasar spectrum. You can see the continuum radiation as well as these spikes, which are the emission lines. And on the right, I have an illustration of mine which shows you what is happening in the quasar as we do reverberation mapping. Whenever the luminosity of the continuum radiation varies, these variations will also occur in the emission lines, but the radiation takes time to travel from the accretion disk to the broadline region, and this will cause the emission lines variations to be delayed. The length of this delay, or tau, allows us to infer the radius of the broadline region. Also, the closer the broadline region is to the black hole, the faster it will be orbiting. As the gases move towards and away from the observer, the radiation emitted gets redshifted and blueshifted, making the emission lines appear wider. Thus, the faster the broadline region is orbiting, the greater the emission line's width, designated by delta V, will be. So what we do is we measure the length of the delay between the emission lines and the continuum radiation. Then we calculate the width of the emission line being used, and these will stand for the size and velocity of the broadline region. To give the final mass, we'll plug it into a special formula. F times C times tau times the square of delta V all over G gives us our black hole mass in solar masses. A major campaign in which this technique was employed was SDSS-ORM, a program which is part of the Sloan Digital Sky Survey. 3 telescopes were used to monitor 849 quasars over the span of 7 years, from 2014 to 2020. The main telescope used is located at the Apache Point Observatory in New Mexico, and it's the same one as in the illustration from the last slide. It's capable of observing hundreds of objects at once by a multi-object spectroscopy. Supporting photometry in the visible and infrared bands was performed by the Canada-France Hawaii Telescope and Stewart University's Bok Telescope in Arizona. Here is a plot of black hole masses from previous reverberation mapping projects, mostly before 2014. These observations came from various telescopes across the world, such as Yunnan Observatory in China, the South Africa Large Telescope, and the Australian Dark Energy Survey. A major difference between these projects and SDSS-ORM is that they could only perform single-object spectroscopy, which means they could only analyze one object at once. And as you can see in the plot to the right, most of the objects measured have a very low redshift, particularly the H-beta emitting quasars. There are some other higher redshift quasars, especially those emitting in carbon-4. In astronomy, as with all sciences, it's important to get a good range in parameter space so that we have a good picture of the objects we are analyzing. During my internship, I created an updated figure of black hole masses using data from the SDSS-ORM project. While some of the data I used was stored in simple text-based files, the data from SDSS-ORM was stored in FITS files, a popular format in astronomy. FITS files can contain various forms of data such as tables and images. The table on the left describes some of the numerous properties measured from the quasar spectrums, including redshift and the strengths of the emission lines. And on the right is some of the code I wrote myself to read the FITS files. Specifically, it reads the header, which describes how long the table is and what kinds of data are included. I used the formula shown earlier to calculate masses from delay and line width, and I cross-matched the data from different catalogs to detect repeated measurements, as some objects detected in the first year of observation were detected again over the 7 years SDSSRM took place. Now, we shall begin adding the new measurements from SDSSRM into our figure. We will start with objects with significant measurements for the H-beta line, as these have the lowest redshift. There were 86 such objects, with 18 of them having repeated measurements. These objects have masses from around 10 million to 8 billion solar masses, with a maximum look-back time of 8 billion years. This refers to how much time it took for light to travel to us from the quasar. It's connected to how much the light had been redshifted due to the universe's expansion. Next, there were 160 objects displaying significant measurements for the MG2 line, 22 of which had repeated measurements. Their masses range from around 10 million to over 10 billion solar masses, and they are up to 11 billion years old. Already, we have now covered much of the parameter space not covered by the previous RM projects, but we are not done yet. 140 objects had measurements in the carbon-4 emission line, and 17 had repeated measurements. They occupy a range of masses somewhat higher than the MG2 masses, from 100 million to over 10 billion solar masses. These objects also have the highest redshifts of all, meaning that we are observing quasars from the universe's earliest years. Finally, there were 23 objects with measurements in the H-alpha line. These occupy a similar range of masses to the H-beta objects but have a slightly lower redshift. I've added a second figure on the right which shows some other properties of the quasars. The x-axis represents the ratio of the iron 2 line to the strength of the H-beta line. And this is related to the accretion rate of the black hole, that is, how much mass it is sucking up. The y-axis represents the width of the H-beta line, which is connected to the orientation of the quasar. And some of you might notice that there are no points for carbon-4. This is because objects for which iron 2 and H-beta measurements were absent were filtered out. The carbon-4 line is in the ultraviolet range, but we're doing observations in infrared and visible light. To detect carbon-4, the spectrum has to be heavily redshifted, but this causes the iron 2 and H-beta lines to be out of range. There are potentially objects with lower redshifts which are also active in carbon-4, but to detect these we'll need to utilize a telescope operating in the ultraviolet range, such as the Hubble Space Telescope. In conclusion, reverberation mapping is an effective technique for calculating black hole masses of distant quasars which we cannot directly image. And with the multi-object spectroscopy capabilities of SDSSRM, we have been able to apply this technique to numerous quasars. But as the lack of certain types of data for the carbon-4 object shows, we still have more observations to make in various areas, and future projects will allow us to collect additional data. I would like to say that I am grateful for this chance to meet with NASA scientists and other interns, and I thoroughly enjoyed working on this project with my mentor Yasmin. I learned a lot about quasars from her and got to put my coding skills to good use. It is great to know that my work will contribute to our understanding of these astronomical objects. With all of that being said, feel free to ask any questions you might have.